All right, so in the last video, we introduced the idea of a proof by contradiction, and now we just need to see several more examples. So in this video, we're going to look at another example, which will involve sets operations. So this is proposition 7.3. So we just want to see the proof by contradiction in several different settings. So for instance, if A and B are sets, then A intersect B set minus A is equal to the empty set. And this should be somewhat intuitive, right? Because you feel like if you take away A from B, then there should be no elements of A and B. If you intersect it with A, those are supposed to be the elements which are in common, and there shouldn't be anything in common, right? So again, this is not a terribly deep statement, but it's a good, simple statement to work with to play around with proofs by contradiction. So let me just draw a simple picture, right, to make sure we're on the same page here. When we do these set operations, we can have A and B, and of course, B set minus A is everything in here, right? So this would be B set minus A. So yeah, if we take B set minus A and intersect it with A, this picture seems to be suggesting, and we'll prove here shortly that that is the case. Now, technically, I want you to see that this proposition is stated in the form of a implication, right? It says if A and B are sets, then A intersect B set minus A is equal to the empty set. And so again, we said that the negation of an implication is logically equivalent to P and not Q. So what does that mean in this case? We're going to assume that A and B are sets. We don't want to negate that. What does it mean to say A and B are not sets? That doesn't seem like a good thing. How do I work with not sets, right? But anyway, so we're going to assume A and B are sets, but we're going to assume the opposite of the conclusion, right? Which is that A intersect B set minus A is not equal to the empty set. And again, the reason why that's going to be helpful is because if it's not equal to the empty set, then there must be something in it, and it gives us something to work with. And I want to keep emphasizing this. Usually a proof by contradiction, the reason why we think to do a proof by contradiction is because we notice that if we make the contradictory hypothesis, we get something to work with, right? And that's what we need to make a proof. So, okay, let's look at the proof. So assume, for sake of contradiction, that A intersect B set minus A is not equal to the empty set. Notice I don't even restate A and B are sets because it's so natural to the setting that I don't even feel like I need to say it again, though you could say it again if you want. But what we do need to assume is the opposite of Q, which in this case is that A intersect B set minus A is not equal to the empty set. So what does that mean, right? That means then there exists some X in A intersect B set minus A. Okay, so again, that gives us something to work with, and now we're just going to unravel the definitions here and see that this is a problem. So by the definition, by the definition of intersection, this implies, well, it implies that X is in A and X is in B set minus A. Okay, now by the definition of set subtraction, X in B set minus A means that X is in B and X is not in A, right? And now we're done basically, right? So we see that X is in A and X is not in A, which is a contradiction. I mean, that already is a clear contradiction to the law of excluded middle because you can't both be something and not something. And this is basically what they're saying. You're in a set and you're not in a set. So this is a contradiction. Oftentimes, if we want to do this informally, we'll write this symbol after the contradiction. And so hence we have found that A intersect B set minus A must be equal to the empty set. Okay, good. So that's our second example of a proof by contradiction, and we'll see several more, but I hope that you're starting to get the idea. And now we just need to start ramping up the difficulty of the proof to try to start seeing more and more sophisticated versions of proofs by contradiction.